The universe holds secrets your textbooks never mentioned. We are about to journey through 30 astonishing space facts that classrooms simply do not have time to teach. You will discover truths about our solar system, and beyond that will permanently alter how you see the night sky. How can a day last longer than a year? What is a planet made of diamond actually like? By the end, the cosmos will feel stranger and more wonderful than you ever thought possible. Are you ready to have everything you thought you knew about space turned upside down? Our very own moon is in the process of leaving us. Right now, as you read this, it is slowly drifting away from Earth at a rate of roughly 3.8 centimeters every single year. That is about the same speed your fingernails grow. The force behind this celestial retreat is the tidal dance between Earth and its satellite. The moon's gravity pulls on our oceans, creating the bulges we know as tides, but Earth's rotation drags that watery bulge slightly ahead of the moon. This offset bulge, in turn, exerts its own gravitational tug, pulling the moon forward in its orbit and giving it a tiny energy boost. The result is a gentle but relentless push, causing the moon to spiral outward year after year. The implications of this slow-motion departure are profound and stretch across cosmic time. In about 600 million years, the moon will have drifted just far enough that total solar eclipses, those breathtaking moments of daytime darkness, will become impossible. The moon's disk will appear too small in our sky to completely cover the sun, and the story does not end there. This tidal friction is a two-way street. While it pushes the moon away, it also acts as a brake on Earth's rotation. Our planet's spin is gradually slowing down, making our days longer. Billions of years from now, a single Earth day could last as long as a month is today. The cosmic clock is ticking, and our closest companion is on a silent journey into a more distant future. This gradual retreat of the moon is a quiet testament to the dynamic forces constantly reshaping our solar system, forces that can create environments of breathtaking violence. If you think Earth's weather is extreme, you have not met the atmosphere of Venus. While the planet itself is a sluggish rotator, taking 243 Earth days to complete a single, agonizingly slow spin, its upper atmosphere is caught in a frenzied sprint. High above the scorching surface, hurricane-force winds scream around the planet at speeds up to 360 kilometers per hour. This phenomenon is called superrotation, and it means the atmosphere itself circles Venus in a mere 4 Earth days, moving 60 times faster than the ground below. Imagine standing in a place where the sky itself is a blur, racing past a landscape that barely seems to move at all. The driving force behind this perpetual atmospheric hurricane remains one of planetary science's great puzzles. Scientists believe the intense heat from the sun, absorbed by Venus's thick carbon dioxide blanket, creates massive temperature differences between the day and night sides. This thermal energy is converted into kinetic energy, powering those relentless winds. The chaos does not stop there. At both of Venus's poles, this super-rotating atmosphere funnels into colossal, permanent vortexes, swirling storm systems that rage endlessly over the poles. They are not like the transient hurricanes of Earth. These are permanent fixtures, planet-wide engines of wind driven by a mystery we are still striving to fully understand. While Venus churns with permanent storms, the depths of space hold a different kind of chemical marvel. Drifting near the heart of our Milky Way galaxy is an interstellar cloud of staggering proportions and an unexpected composition. Known as Sagittarius B2, this colossal molecular cloud contains, among many other compounds, vast quantities of vinyl alcohol. To be clear, this is not the kind of alcohol you would find in a drink, but its existence is no less intoxicating for scientists. The cloud is estimated to hold enough of this organic molecule to create billions upon billions of liters of the substance. How does something so complex form in the cold, sparse vacuum between stars? The process begins in the outer layers of aging stars, where simple molecules are forged and then cast off into space. Inside these immense clouds of gas and dust, atoms and simple molecules collide, sometimes sticking together. Shielded within the dusty heart of the cloud, away from harsh stellar radiation, these particles can slowly, over millions of years, assemble into more complex organic structures on the surfaces of dust grains. The discovery of vinyl alcohol and many other complex organics in Sagittarius B2 is a revelation. It tells us that the fundamental chemical ingredients for life, the very building blocks, are not unique to Earth. They are being manufactured in factories of gas and dust scattered throughout the galaxy, raining down on young planets as they form. This means that wherever conditions are right in the cosmos, the raw materials for life may already be present, a cosmic inheritance written in the chemistry of the stars themselves. That same sluggish rotation holds another bizarre record. A single day on Venus, the time it takes for the planet to spin once completely on its axis, is actually longer than an entire Venusian year. To put that in perspective, if you could stand on that scorching surface, you would celebrate your birthday before you ever saw the sun rise and set just once. The numbers are staggering. Venus requires 243 Earth days to complete a single rotation. Yet, it only takes 225 Earth days to complete a full journey around the Sun. This means a day on Venus lasts 18 Earth days longer than its year. This slow waltz is made even stranger by its direction. Venus rotates backwards, a motion astronomers call retrograde rotation. While most planets in our solar system spin counterclockwise when viewed from above the North Pole, Venus spins clockwise. Imagine a top spinning in the opposite direction of everything around it. The cause of this backward, snail's pace spin is a subject of intense study. The leading theory suggests that in the chaotic early solar system, a colossal impact with another large object could have literally knocked Venus upside down, reversing its spin and slowing it to this glacial crawl. This incredibly slow rotation has dramatic consequences for the planet itself. Without a fast-spinning molten core to generate a planetary dynamo, Venus lacks a global magnetic field like Earth. That missing shield leaves its atmosphere exposed to the full fury of the solar wind, which over eons has stripped away lighter elements and helped bake the planet into the oppressive, high-pressure oven it is today. Time itself is distorted there, measured in a rhythm utterly alien to our own. The cosmic chemistry that seeds life begins in stellar furnaces, but some stars meet a far more extreme fate. When a truly massive star reaches the end of its life, it does not fade quietly. It explodes in a supernova of unimaginable power, blasting its outer layers into space. What remains is not a white dwarf, but something infinitely stranger and denser. The core collapses under its own immense gravity, crushing atoms themselves. Electrons are forced into protons, and everything fuses into a sea of pure neutrons. This is a neutron star, the densest, most compact form of matter we know exists in the universe. To grasp its impossible density, consider this. A single sugar cube worth of neutron star material would weigh over 1 billion tons here on Earth, as much as an entire mountain. An entire object with more mass than our Sun is squeezed into a perfect sphere only about 20 kilometers across, the size of a modest city. If you could stand on its surface and survive the forces at play, you would be looking up at a sky where the curvature is so severe the entire horizon would wrap around you, the stars distorted into bizarre rings by gravity bending light itself. Some neutron stars reveal themselves through rhythmic pulses of radiation, sweeping across the cosmos like celestial lighthouses. We call these pulsars. As the star spins, sometimes hundreds of times per second, beams of energy from its magnetic poles slice through space. If one of those beams points toward Earth, our telescopes detect a perfectly timed flash with every rotation, a metronome of unmatched precision. But these are not placid objects. Their crystalline crusts, harder than diamond, can crack under immense strain. These starquakes or glitches can cause the pulsar's spin to suddenly increase in a fraction of a second, releasing more energy than our sun will emit in 100,000 years. The magnetic fields surrounding some neutron stars are so intense they could wipe a credit card clean from halfway to the moon. They are nature's ultimate physics laboratories, places where matter exists in a state we can never replicate, governed by laws that push the very boundaries of our understanding. Even the mightiest volcanoes on Earth are mere foothills compared to the true titan of our solar system. On the rust-colored plains of Mars, a single mountain named Olympus Mons reigns supreme. This is not just a large volcano, it is a geological monument of staggering scale. Olympus Mons is a shield volcano, a type formed by the gentle flow of low-viscosity lava over immense periods. Its gentle slopes belie its true size. From base to summit, Olympus Mons stands nearly 22 kilometers high. That is almost 3 times the height of Mount Everest. But its true majesty is in its breadth. The entire volcano is roughly the size of the state of Arizona, its base sprawling over an area 600 kilometers wide. To stand at its peak would be to stand on a world within a world, the curvature of Mars visibly dropping away beneath you into a caldera complex so vast entire cities could fit inside its chasms. The secret to its colossal growth lies in a fundamental difference between Mars and Earth. Our planet is alive with plate tectonics, where the crust is a shifting puzzle of moving plates. A hot spot of magma will burn through the crust, creating a volcano, but as the plate slowly drifts, the volcano moves off the hot spot and becomes dormant while a new one forms nearby. This is how the Hawaiian Islands formed, a chain of volcanoes created by a single hotspot as the Pacific plate drifted over it. Mars, however, has a single static crust. For billions of years, a single stationary plume of magma rose from the Martian mantle to the same spot on the surface. With no tectonic plates to shift the landscape, the lava simply kept piling up in the same location, layer upon layer, millennium after millennium, building a mountain of such immensity it dwarfs every other landform we know. Olympus Mons is a fossil of a more volcanically active Mars, a permanent record of a planet's fiery heart beating in one spot for eons, creating a monument that will likely never be rivaled. The profound silence of a neutron star is an illusion our human senses create. We have all heard the phrase, "In space, no one can hear you scream," and this is technically true. Sound, as we understand it, requires a medium like air or water to travel, molecules bumping into each other to carry a wave. The near-perfect vacuum between stars offers no such highway for these vibrations. But to say space is silent is to misunderstand it completely. Space is not mute, it is broadcasting on a frequency our ears are not built to hear. Every planet, star, and nebula emits a constant torrent of electromagnetic radiation, from radio waves to X-rays. Scientists have found a remarkable way to translate this invisible symphony into something we can experience: sonification. They take the data, the intensity and frequency of these emissions, and map them directly to audible sounds. The results are haunting and beautiful. Saturn's rings, for instance, produce a chorus of whistles and static, the sound of countless particles colliding, captured by the Cassini spacecraft as it dove through them. The pulsar at the heart of the Crab Nebula becomes a relentless, rhythmic heartbeat, each pulse a flash of radiation turned into a percussive click. Perhaps most profound is the sound of the cosmic microwave background, the faint afterglow of the Big Bang itself. When sonified, it is a deep, rumbling roar, the foundational note of our universe stretched across an unimaginable spectrum. Listening to these sounds does more than satisfy curiosity. It allows us to perceive cosmic phenomena in an entirely new, visceral way. It turns abstract data into an experience, letting us hear the solar wind wash over a planet or feel the steady tick of a cosmic clock. the universe is not quiet, it is a concert of energy, and we are only just beginning to learn how to listen. This cosmic symphony of energy finds its most intense source right at the heart of our own solar system, yet the Sun holds a paradox that defies common sense. The visible surface of the Sun, the glowing disk we see in the sky called the photosphere, has a temperature of about 5,500 degrees Celsius. It is a searing, unimaginable heat, but if you travel outward from that surface into the wispy outer atmosphere known as the corona, the temperature does not drop. It skyrockets. The corona routinely reaches temperatures of 1 to 2 million degrees Celsius, hundreds of times hotter than the surface below. This is the coronal heating problem, one of the longest-standing mysteries in solar physics. How can the atmosphere be so much hotter than the furnace it surrounds? It is like walking away from a bonfire and suddenly stepping into an inferno. The answer is not in simple radiant heat, but in the Sun's invisible architecture of magnetic fields. Our star is not a placid ball of gas, it is a churning, dynamic entity. Its magnetic field is constantly tangled, twisted, and stretched by the different rotation rates at its equator and poles. Scientists believe two main processes may be responsible for transferring immense energy into the corona. The first is magnetic reconnection. Imagine two powerful magnetic field lines stressed like overstretched rubber bands, snapping and reconnecting in a new configuration. This sudden snap releases a colossal amount of stored magnetic energy in a violent burst, heating the surrounding plasma to extreme temperatures. The second candidate is the constant rain of nanoflares. These are not the massive solar flares we see, but countless tiny, explosive events, each a miniature magnetic reconnection happening all across the Sun. Individually, they are too small for our telescopes to see, but together they could provide a continuous drizzle of energy, a perpetual heating system for the corona. Observatories like NASA's Solar Dynamics Observatory and the Parker Solar Probe, which has flown through the corona itself, are gathering the data to solve this puzzle. They reveal a corona that is not a placid halo, but a seething, dynamic realm of magnetic loops and constant activity. Solving this mystery is not just academic, it is crucial. The superheated corona is the source of the solar wind, that stream of charged particles that washes over our planet. Understanding how it heats up helps us predict space weather, protecting our satellites and power grids from the Sun's most violent moods. The star that gives us life is still teaching us fundamental lessons about how the universe works. Such extreme heat and pressure in a stellar core can forge wonders far beyond our imagination, including a world of almost pure crystal. Orbiting a rapidly spinning pulsar 20,000 light-years away lies a planet unlike any other in our solar system, a world astronomers believe is essentially a giant diamond. Known as PSR J 1719-1438b, this exotic planet began its life not as a rocky world like Earth, but as a star itself, likely a white dwarf. Its story is one of cosmic cannibalism and staggering transformation. The pulsar it orbits is the ultra-dense, city-sized remnant of a massive star that went supernova. In the aftermath of that cataclysm, the two stellar remnants, the pulsar and the white dwarf, were locked in a close orbit. The pulsar, with its ferocious gravity and radiation, began relentlessly stripping material away from its companion, whittling the white dwarf down over eons. What remained was an object with a mass slightly greater than that of Jupiter, but compressed into a sphere only about half its size. Under this immense compression, the carbon that made up the white dwarf's core was subjected to pressures and temperatures so extreme that its atomic structure rearranged into a crystalline lattice. The entire planet, scientists conclude, is likely a single massive crystal of carbon, a diamond of stellar proportions. We can detect such a bizarre world not by seeing its faint sparkle, but by listening to the impeccable rhythm of its pulsar parent. Astronomers measure the precise timing of the pulsar's radio pulses. As the diamond planet orbits, it exerts a tiny gravitational tug, causing the pulsar to wobble ever so slightly. This minuscule motion creates a detectable delay in the arrival time of the pulses, a telltale signature that betrays the planet's presence, mass, and orbit. It is a ghostly world revealed only by the perfect metronome of a dead star, a glittering testament to the universe's ability to create treasures from the ashes of stellar violence. The diamond planet is a world forged from a star's demise, but another celestial body in our solar system has been sculpting itself for centuries through pure atmospheric fury. Jupiter's Great Red Spot is not just a storm, it is the longest-lived hurricane we have ever observed, a swirling vortex of gas that has raged for at least 350 years, possibly far longer. When it was first reliably observed in the 1600s, it was estimated to be wide enough to fit 3 Earths side by side. This colossal anticyclone, a high-pressure storm spinning counterclockwise, is a permanent fixture in Jupiter's southern hemisphere, held aloft by the planet's ferocious jet streams and fed by the heat rising from its deep interior. Its iconic crimson color, likely caused by complex chemicals like ammonium hydrosulfide being churned up from deeper layers and broken apart by solar ultraviolet radiation, makes it a stark jewel against the bands of cream, orange, and brown. For generations, we viewed it as a permanent landmark, an eternal feature of the solar system's largest planet. Yet, the landmark is changing. Continuous observations from Earth-based telescopes and spacecraft, from Voyager to Galileo and now Juno, have documented a clear and steady trend. The Great Red Spot is shrinking. Measurements show its east-west width has diminished significantly over the past several decades. Where it once easily engulfed our entire planet, it is now just slightly wider than Earth itself. The storm is not only getting narrower, but it also appears to be becoming more circular, and its iconic color has deepened and intensified in recent years. The question, of course, is why? What could possibly cause a centuries-old atmospheric engine to slowly wind down? Scientists have several compelling theories. One suggests that smaller storms, eddies, and vortices that constantly dance across Jupiter's turbulent face are interacting with the spot's outer edges, acting like atmospheric sandpaper and gradually eroding its momentum, stealing its energy. Another possibility is linked to internal heat. Jupiter radiates more heat than it receives from the Sun, and changes in how this internal warmth is distributed and rises through the layers of the atmosphere could be altering the very fuel that sustains the storm. It might be experiencing a kind of planetary climate change we are only beginning to understand. The potential disappearance of the Great Red Spot would be more than just the loss of a beautiful feature. It would be the end of a natural laboratory that has taught us invaluable lessons about fluid dynamics, weather persistence, and the behavior of atmospheres on a scale we cannot replicate. Studying its slow death could provide critical clues about the stability of giant planet weather systems and the complex interplay of forces that govern them. Will it vanish completely in our lifetimes, or will it stabilize at a new, smaller equilibrium? Its fate remains one of the great ongoing dramas in our solar system, a reminder that even the most ancient and seemingly permanent features of the cosmos are participants in a constant, dynamic dance of creation and decay. While Jupiter's storm rages at hundreds of degrees, the cosmos also harbors celestial bodies with a startlingly gentle nature. Littering the galaxy are countless objects known as brown dwarfs, often called failed stars. They form from collapsing clouds of gas and dust, just like stars, but they never gather enough mass to cross a critical threshold. Inside a true star, the crushing weight and heat at the core become so intense that they ignite the sustained nuclear fusion of hydrogen into helium, the process that makes a star shine. Brown dwarfs fall short. They are too small, with masses typically between 13 and 80 times that of Jupiter. This means their cores never reach the millions of degrees required for that sustained hydrogen fusion furnace. Instead, they glow with a dim, residual heat from their violent formation and from brief, feeble fusion of deuterium, a heavy isotope of hydrogen which burns out relatively quickly. After that, they simply cool down over billions of years, fading from a dull red ember to a planet-like object. The most astonishing fact is just how cool they can become. While some are scorching hot, the oldest, coldest brown dwarfs have surface temperatures comparable to a pleasant day on Earth, some even as low as room temperature. In theory, if you could somehow approach one and survive the gravitational and atmospheric pressures, you could touch its gaseous surface without being incinerated. Finding these faint, almost dark objects is a monumental challenge for astronomers. They emit almost no visible light, only a faint whisper of infrared radiation, the warmth of their slow cooling. They are discovered by painstakingly scanning the sky with powerful infrared telescopes, looking for single points of dim heat that are not associated with any visible star. Each discovery is a triumph of technology and patience. Studying these cosmic in-betweeners is crucial because they blur the line we try to draw between giant planets and tiny stars. They share characteristics with both. Like planets, they can have complex, cloudy atmospheres with storms and weather patterns. Like stars, they form on their own from a collapsing cloud. They represent a missing link, a population of objects that help us understand the entire spectrum of celestial formation, from the largest gas giants to the smallest red dwarf stars. Their quiet, cool existence reminds us that the universe contains not just infernos and explosions, but also slow, fading embers that challenge our very definitions. The quiet, unchanging nature of a brown dwarf stands in stark contrast to the dynamic surface of our own moon, where a different kind of permanence has been left behind. On that gray, dusty world, the footprints of the 12 Apollo astronauts who walked there are not fading. In fact, they will likely remain visible and perfectly preserved for millions of years to come. This is not a metaphor for human legacy, but a literal, physical truth. The moon is a world frozen in time. It lacks the very forces that erase history on Earth. There is no wind to scatter the fine lunar soil called regolith. There is no flowing water to smooth over impressions or wash them away. There is no significant geological activity, no shifting tectonic plates or volcanic flows to bury the sites. The only processes at work are incredibly slow. Micrometeorite impacts, a constant gentle rain of tiny space dust, will very gradually churn the top layer of soil over eons. But this is a process measured in millions of years. The sharp, crisp treads left by Neil Armstrong and Buzz Aldrin in 1969, the sweeping arcs of the lunar roving vehicle tires, even the discarded descent stages of the lunar modules all sit in a profound and eerie silence. They are a time capsule of humanity's first steps off our home planet, an archaeological site of unparalleled significance. Think of the lengths we go to preserve ancient footprints here on Earth, like the Litoli footprints in Tanzania, pressed into volcanic ash 3.6 million years ago. We build shelters over them, control the environment. On the moon, the entire environment is the preservation chamber. The vacuum of space prevents oxidation or chemical decay. The temperature extremes, while dramatic, do not cause erosion in the way we understand it. These sites are more than historical landmarks, they are scientific instruments. By returning to them, future missions could study how the regolith has been altered by decades of exposure to the solar wind and cosmic rays, using the original footprints and equipment as a baseline. They stand as a testament to a moment when a species looked up, dared to reach, and left an indelible mark on another world. A mark that will outlast mountains, civilizations, and perhaps even the human race itself. The footprints on the moon will endure in a perfect vacuum, but another world much closer to the sun hides its own frozen secret in absolute darkness. Mercury, the scorched innermost planet, holds water ice at its poles. This seems impossible. With daytime temperatures hot enough to melt lead, how could ice survive? The answer lies in its tilt, or rather, the lack of it. Mercury's axis of rotation is almost perfectly vertical, meaning it has no seasons and no tilted poles pointing toward the Sun. Deep within craters at its north and south poles, there are places where the Sun never rises. The rims of these craters cast permanent shadows, creating pockets of profound cold that dip to -170 degrees Celsius, even as the surrounding plains bake. For decades, ground-based radar telescopes hinted at something highly reflective in these dark zones. Then, NASA messenger spacecraft arrived, confirming the incredible truth. Its instruments mapped the permanently shadowed regions and detected the clear signature of water ice, not just a thin frost, but deposits tens of meters thick in some places. This ice is likely mixed with a dark, organic, rich material that helps insulate it. Where did it come from? The leading theory points to a cosmic delivery service. Comets and water-rich asteroids have been bombarding the inner solar system for billions of years. When one of these objects strikes Mercury, most of the water vaporizes instantly in the heat. But if an impact occurs near the poles, some of that water molecules could hop across the surface, entering a random walk until they stumble into a permanently shadowed crater, where they finally stick, accumulating over eons into a substantial reservoir. The discovery reshapes our understanding of the early solar system. It proves that water, that essential ingredient, was being delivered everywhere, even to the harshest environments. If ice can persist on Mercury, then it could be trapped in similar shadowed craters on our Moon or on countless asteroids. These cold traps become time capsules, preserving a record of the primordial water that helped seed the inner planets. Mercury's hidden ice is a paradox that teaches a profound lesson. Even in the most extreme places, the universe finds a way to preserve the elements of life. The hidden ice of Mercury is a quiet archive of cosmic impacts, but the center of our galaxy hosts a far more active and violent spectacle. Drifting toward the very heart of the Milky Way is a mysterious object known as G2. This was not a star or a planet, but a strange, elongated cloud of gas and dust 3 times the mass of Earth. Its trajectory was clear and inevitable, a cosmic arrow pointing directly at Sagittarius, a star, the supermassive black hole that anchors our galaxy. Astronomers watched with a mix of excitement and dread as calculations showed G2 would make its closest approach, a grazing pass just a hair's breadth from the black hole's event horizon. The expectation was a spectacular cosmic meal. They predicted the cloud would be torn apart by the black hole's immense tidal forces, stretched into a long, thin streamer like cosmic spaghetti in a process called spaghettification. As this material spiraled into the accretion disk, it would heat to millions of degrees, erupting in a brilliant flare of X-rays that would light up the galactic center. This promised a front-row seat to observe how a supermassive black hole feeds, a chance to study the physics of accretion in real time. The telescopes were pointed, the instruments primed. The moment arrived, and then almost nothing happened. G2 made its perilous swing past the point of no return and emerged, battered but largely intact. It was not completely torn apart. This was not the delicate cloud everyone thought. The leading theory now suggests G2 is not a simple wisp of gas at all, but something far more substantial hiding inside. It may be a star shrouded in a thick cloak of gas and dust, perhaps formed from the merger of 2 stars whose combined material created this extended envelope. The gravity of a central stellar core would have provided the internal fortitude to resist being completely shredded by the black hole's grasp. The encounter did create some interaction, a faint brightening, but it was a whisper, not the scream astronomers anticipated. This anticlimax was in its own way a profound discovery. It taught us that the environment around a supermassive black hole is even more complex and populated with strange, hidden objects than we knew. It showed that black holes are not always messy eaters, and that material can sometimes survive a close gravitational dance. The resilience of G2 forced a complete rethink of what can survive in the most extreme neighborhood in the galaxy, revealing that sometimes the greatest mysteries are not in the destruction but in what stubbornly endures. G2's hidden resilience shows that even near a black hole, worlds can cling to existence, but one world in our own solar system has already mastered the art of persistence under alien skies. Far beyond Mercury's ice and Jupiter's storms, orbiting the ringed giant Saturn, is a moon that feels hauntingly familiar. Titan is the only place other than Earth where we have found stable liquid on its surface in vast lakes and flowing rivers. But do not expect to find water there. On Titan, with surface temperatures plunging to -180 degrees Celsius, water is frozen harder than granite. The liquid that fills its lakes and carves its river valleys is methane and ethane, hydrocarbons that are gases on our world but flow like water on that frigid, orange-hazed moon. Titan possesses a full, dynamic hydrologic cycle eerily similar to our own, but built from this alien chemistry. Methane evaporates from the lakes, forms clouds in its thick nitrogen atmosphere, and falls back down as rain, sculpting the landscape over eons. We have seen it firsthand. In 2005, the European Space Agency's Huygens probe detached from the Cassini spacecraft and descended through Titan's opaque, smoggy atmosphere. For 2.5 hours it fell, transmitting data and images back to a breathless audience on Earth. Then it touched down on a damp, pebble-strewn plain, becoming humanity's first landing on a world in the outer solar system. The images it sent back in its final minutes of operation were surreal, showing a landscape of rounded ice rocks set against a murky orange sky, a scene both utterly alien and strangely reminiscent of a rocky creek bed on Earth. Beyond its rivers, Titan may harbor another familiar feature, cryovolcanoes. Instead of spewing molten rock, these volcanoes would erupt a chilly slurry of water ice, ammonia, and other compounds, a process that could replenish the atmosphere with methane and reshape the terrain. This leads to the most compelling reason we study Titan, its profound potential for probiotic chemistry, the steps that lead to life. Its thick atmosphere, rich in organic molecules, and its liquid methane seas provide a vast natural laboratory for chemical reactions. Sunlight breaking apart methane high in the atmosphere creates a cascade of more complex hydrocarbons which rain down onto the surface. These are the same kinds of organic building blocks that existed on the early Earth before life emerged. Could those same processes, playing out with different solvents and at vastly colder temperatures, lead to a form of life we have never imagined? Titan forces us to broaden our definition of a habitable world. Life as we know it requires liquid water, but Titan asks a thrilling question. Could a different biochemistry, one based on liquid methane, arise? Its lakes may not be water, but they are a cradle, holding the possibility that we are not alone, and that life, in forms beyond our wildest dreams, might be waiting in the cold, dark rivers of an alien moon. The possibility of life on a frigid moon like Titan depends on a stable cosmic environment, but the universe itself is undergoing a change so profound it will ultimately rewrite the fate of everything. For nearly a century, we have known the universe is expanding, a legacy of the Big Bang. Distant galaxies are all rushing away from us, their light stretched into redder wavelengths. The logical assumption was that this expansion must be slowing down over time, pulled by the collective gravity of all the matter in the cosmos. It was a cosmic brake pedal, gradually easing the universe's outward rush. Then, in the late 1990s, two independent teams of astronomers made a discovery so shocking it would win them the Nobel Prize. They were measuring the distances and recession speeds of extremely far-off supernova, using them as cosmic mile markers. They expected to see that the expansion was decelerating. Instead, they found the opposite. The most distant galaxies were receding faster than predicted. The expansion of the universe is not slowing down, it is accelerating. It is as if you tossed a ball into the air, expecting it to fall back, only to watch it shoot upward faster and faster into the sky, defying gravity itself. This meant something was actively working against gravity's pull, a mysterious, repulsive force permeating the fabric of space itself. We call this force dark energy. It is not a substance we can see or touch, but rather a property of empty space, a kind of latent pressure that causes the universe to stretch apart at an ever-increasing rate. Current measurements suggest dark energy constitutes about 68% of the entire cosmos, dwarfing the 5% of normal matter and the 27% of dark matter that makes up galaxies. Its nature remains one of the greatest unsolved puzzles in physics. Is it a cosmological constant, as Einstein once proposed and then discarded, a fixed energy density of the vacuum? Or is it something more dynamic, a field that evolves over time? We simply do not know, but we do know its ultimate consequence for our cosmic future. If this acceleration continues unchecked, it leads to a profoundly lonely destiny known as the Big Freeze. Over trillions of years, as space itself stretches faster and faster, distant galaxies will be carried beyond our observable horizon, their light no longer able to reach us. The night sky, currently filled with the faint glow of countless galaxies, will gradually go dark, leaving only the stars of our own Milky Way and its eventual merger partners. Eventually, even star formation will cease as the raw material is locked away in dead stars and black holes. The universe will become a vast, cold, and ever more empty expanse, with isolated islands of matter drifting forever apart in an eternal, expanding silence. This accelerating expansion is not just a distant fact, it is the engine driving the ultimate fate of reality, a silent force we have only just begun to perceive. While dark energy pushes the universe apart on the grandest scale, a gravitational mystery much closer to home continues to pull at the edges of our own solar system. Far beyond Neptune, in the cold, dark realm of the Kuiper Belt, something strange is happening. This distant belt of icy bodies, home to Pluto and countless other worldlets, should be a place of random, disordered orbits. Yet astronomers have discovered a small group of these extreme trans-Neptunian objects whose orbits are not random at all. Their elongated paths are mysteriously clustered, all tilted in the same direction and swooping out to their greatest distances in the same general part of the sky. This is not what you would expect from chance alone. It is as if you dropped a handful of marbles on the floor and they all rolled to the same corner and lined up neatly. The gravitational pull of the known giant planets cannot explain this peculiar alignment. The most compelling explanation is the gravitational hand of an unseen world, a hypothetical giant we call Planet 9. This proposed planet is not a small rock but a true giant, estimated to have a mass between 5 and 10 times that of Earth, making it a super-Earth or a mini-Neptune. Its orbit would be immense and highly elliptical, taking it on a lonely, staggering journey around the Sun. At its closest approach, it might come within 200 or 300 times the Earth-Sun distance, but at its most distant, it could swing out over 1,000 times that far, taking perhaps 10,000 to 20,000 years to complete a single orbit. This incredible distance and its faint reflected sunlight are why we have not seen it yet. The search for Planet 9 is a modern astronomical detective story, using the subtle clues left in the paths of smaller objects to infer the presence of a hidden giant. Teams of astronomers are methodically scanning the predicted regions of the sky with the world's most powerful telescopes, like Subaru in Hawaii, trying to catch its faint glimmer. Every new discovery of a distant Kuiper Belt object with a peculiar orbit adds another data point, refining the possible location of this ghost world. The implications of finding it would be monumental. It would be the first true discovery of a major planet in our solar system in over 170 years, since Neptune was pinpointed by similar mathematical prediction. Its existence would force us to rewrite the story of our solar system's formation and early migration. How did such a large planet get flung into such a distant, tilted orbit? Was it captured from another star system in the Sun's infancy, or was it ejected outward in a chaotic gravitational dance with Jupiter and Saturn? Until a telescope finally captures its light, Planet 9 remains a tantalizing shadow at the edge of everything we know, a gravitational signature written in the ice waiting to be seen. Two human-made objects are now sailing through the interstellar void. Voyager 1 and Voyager 2, launched in 1977, have officially left the protective bubble of our Sun. They crossed a boundary called the heliopause, the point where the outward pressure of the solar wind finally gives way to the winds from other stars. It is a frontier we can only visit through these two intrepid explorers. Voyager 1 made the historic crossing in August of 2012, with Voyager 2 following in November of 2018. Their instruments recorded the moment, a sudden drop in particles from our Sun, and a corresponding rise in cosmic rays from the galaxy. They are now in a region no spacecraft has ever been, measuring the true characteristics of the space between stars. But their journey is about more than data. Each probe carries a time capsule, a 12-inch gold-plated copper disc known as the Golden Record. It is a message in a bottle cast into the cosmic ocean. The records contain sounds and images selected to portray the diversity of life and culture on Earth. There are greetings in 55 languages, from ancient Akkadian to modern Wu. The sounds of a baby crying, a heartbeat, a kiss, and thunder. Music ranging from Bach and Beethoven to Chuck Berry and traditional Senegalese drums. And 115 images encoded in analog form, showing everything from mathematical diagrams and DNA structures to scenes of families, cities, and our planet from space. They are a snapshot of humanity, intended for any civilization that might find them billions of years from now. Today, over 45 years after launch, we still hear from them. Their signals, now a faint whisper at less than a watt of power, take over 20 hours to travel back to Earth at the speed of light. The dedicated teams at NASA, a deep space network, listen intently, receiving precious bits of data about the magnetic fields and plasma density in this uncharted territory. The probes are teaching us that the boundary of our solar system is not a sharp wall, but a complex, rippling interface, a cosmic shore where the Sun's influence ebbs and flows. Their nuclear batteries will likely keep them communicating until around 2030, after which they will fall silent, destined to drift among the stars forever. Long after their last signal fades, they will continue their mission, carrying the story of a curious species that once looked up and sent its whispers into the dark. Earth's gravity does not hold just one moon in its sway. Our planet occasionally captures a second, fleeting companion from the depths of space. These are minimoons, small asteroids, typically just a few meters across, that get snagged by Earth's gravitational pull and enter a temporary, chaotic orbit around us. Unlike our permanent moon, these visitors are not bound for the long term. They are cosmic hitchhikers, staying for a few months or years before the complex interplay of gravitational forces from the Earth, Moon, and Sun flings them back out into the solar system. For decades, they were only a theoretical possibility, too small and faint for our telescopes to spot. That changed in February of 2020. Astronomers with the Catalina Sky Survey in Arizona detected a faint, moving speck of light. It was not a satellite, and its path was unmistakable. They had found an object, later named 2020 CD3, that was already in orbit around Earth. This car-sized asteroid, likely no more than 3 to 6 meters in diameter, had been circling our planet undetected for nearly 3 years before its discovery. Its orbit was a wide, wobbly dance, taking it from roughly as close as the Moon to more than twice that distance. For a brief period, we truly had two moons. The discovery was monumental, not for its visual spectacle, but for its scientific promise. A minimoon is a unique gift from the cosmos. It is an asteroid delivered practically to our doorstep, requiring a fraction of the energy to reach compared to targets in the main asteroid belt. Studying one up close would give us a pristine sample of the building blocks of the solar system. We could analyze its composition, structure, and history without the immense cost and time of a deep space mission. Furthermore, these objects represent a potential future resource. A small, captured asteroid could, in theory, be mined for water ice, which can be split into hydrogen and oxygen for rocket fuel or for valuable metals. They could serve as stepping stones and fueling depots for deeper space exploration. In April of 2020, CD3 was given a gentle gravitational nudge and drifted away, resuming its journey around the Sun. Its departure reminds us that our celestial neighborhood is dynamic. We do not sit in static isolation, but in a cosmic crossroads where rubble from the solar system's construction occasionally drops in for a visit. The hunt is now on for the next temporary moon, a chance to reach out and touch a piece of the ancient solar system as it passes by our door. These temporary moons are fleeting visitors, but the cosmos also holds ancient residents whose very existence once seemed to contradict reality. Nestled in our own galactic neighborhood, a star known as HD 140283, nicknamed the Methuselah star, presented astronomers with an impossible puzzle. Initial measurements of its age suggested it was a staggering 16 billion years old. This was a profound problem because the best estimates for the age of the universe itself, based on the expansion rate and the cosmic microwave background, are approximately 13.8 billion years. How could a star be older than the cosmos that birthed it? This was not a small margin of error. It was a paradox that threatened to unravel our understanding of cosmic history. The age of a star is not read from a birth certificate. It is pieced together through careful detective work. For the Methuselah star, astronomers used its brightness, temperature, and most crucially, its chemical composition. It is a metal-poor star, meaning it contains very low amounts of elements heavier than hydrogen and helium. In the early universe, only these lightest elements existed, forged in the Big Bang. Heavier elements like iron and carbon were cooked later inside the first generations of massive stars and scattered by their supernova explosions. Therefore, a star with extremely low metal content must have formed from nearly pristine material, making it one of the first stars to ignite after the Big Bang, a true cosmic elder. The initial 16 billion-year estimate came from sophisticated computer models of stellar evolution, but those models had subtle uncertainties. The key to resolving the paradox lay in refining every single measurement. Using the Hubble Space Telescope, astronomers pinned down the star's distance with exquisite precision, which allowed for a more accurate calculation of its intrinsic brightness, a critical factor. They also improved their models to account for the star's exact mixture of oxygen and iron, which affects how it burns fuel and ages. With these refined inputs, the estimated age of the Methuselah star dropped. The latest calculations place it at around 14.5 billion years old, give or take 800 million years. This brings it into alignment with the age of the universe, though just barely, its margin of error still brushing up against the cosmic dawn. The resolution of this paradox did more than just fix a number. It showcased the remarkable precision of modern astronomy and the iterative nature of science. It also highlighted a thrilling truth: we have indeed found stars that formed when the universe was in its infancy. The Methuselah star is a living fossil, a beacon from a time when galaxies were first assembling, and its light carries the untold stories of that primordial era. Its very existence, now reconciled with cosmic history, stands as a testament to the first flickers of starlight that began to illuminate the dark, expanding cosmos. The Methuselah star witnessed the first dawn of light, but some planets are born into a sky with two. Forget the single sun of our solar system. Imagine a world where double sunsets paint the horizon. These are circumbinary planets, worlds that orbit not one star but two, locked in a gravitational dance around both. The most famous of these is Kepler 16b, a cold, Saturn-sized world discovered by the Kepler Space Telescope. Its existence proved that planets could form and survive in the chaotic environment of a binary star system, a scenario once thought too unstable for worlds to coalesce. In the Kepler 16 system, the two stars themselves are a close-knit pair, waltzing around each other every 41 days. The planet orbits this dancing duo at a much greater distance, taking about 229 days to complete a year. From the surface of such a world, the view would be straight out of science fiction. You would see two distinct suns, one larger and orange-tinted, the other smaller and redder, chasing each other across the sky in a perpetual celestial ballet. Their light would cast complex, shifting shadows, and a single day would have periods of single, double, and even overlapping sunlight. The stability of such an orbit is a delicate puzzle. A planet cannot simply circle between two stars, it would be violently ejected. Instead, it must orbit far enough outside the binary pair's center of mass, tracing a wide, smooth path around both stars together. This requires a precise distance, a Goldilocks zone of orbital dynamics where the gravitational tugs from the two stars balance out into a stable, circumbinary path. Finding these worlds is an extraordinary feat of detection. The primary method used by Kepler is the transit method, watching for the tiny dip in starlight as a planet passes in front of its star. In a binary system, the light curve becomes a tangled web of signals. The two stars eclipse each other regularly, creating periodic dips. A planet transiting across one, or sometimes both, stars adds another layer of subtle, irregular dimming. Astronomers must untangle this complex signal from the noise, a process akin to identifying a single, specific whisper in a roaring crowd. The discovery of Kepler 16b and dozens of other circumbinary planets since has profound implications. It tells us that planet formation is not a fragile process confined to serene, single-star nurseries. It is a robust, almost stubborn force of nature that can proceed even in the turbulent disk of material surrounding two young stars. These Tatooine planets, as they are affectionately called, dramatically expand the real estate of the cosmos. Given that a majority of stars in the galaxy are found in binary or multiple systems, the number of potential homes for planets just grew exponentially. Their very existence is a testament to the dynamic and diverse architectures of solar systems, proving that the universe's imagination far exceeds our own, crafting worlds under double suns where the sky itself tells a story of perpetual motion. Our galaxy is not an island drifting in solitude, but a ship on a long and inevitable course toward a titanic meeting. The Milky Way is on a collision course with its nearest large galactic neighbor, the Andromeda Galaxy. This is not speculation, but a certainty confirmed by precise Hubble Space Telescope measurements of Andromeda's motion. Yet there is no cause for alarm in any human timescale. This cosmic rendezvous is scheduled for about 4.5 billion years from now, long after our Sun has swelled into a red giant and transformed the inner solar system. The process itself will be a slow-motion ballet of staggering proportions, unfolding over billions of years. As Andromeda, which is actually larger than our Milky Way, draws nearer, it will first appear as a faint, elongated smudge in the night sky, growing steadily brighter and larger. Over eons, the two great spiral structures will begin to distort each other's shapes, their mutual gravity pulling out vast streams of stars and gas in long, luminous tidal tails. From a hypothetical future Earth, the view would be breathtaking and utterly alien. The familiar band of the Milky Way would be warped and intertwined with another, brighter band of light, filling much of the sky with a chaotic, brilliant tapestry. The core of Andromeda would blaze as a second, intense hub of stars. Crucially, this will not be a cataclysm of colliding stars. The spaces between stars are so unimaginably vast that direct stellar collisions are exceedingly unlikely. Stars will simply pass by one another, like two vast swarms of bees flying through each other, their individual paths gently redirected by gravity. The real violence will be reserved for the gas and dust clouds within both galaxies. These will slam together, compressing and triggering furious waves of new star formation, lighting up the merging galaxies with the blue blaze of stellar nurseries. After perhaps 2 billion years of this gravitational dance, the two galaxies will complete their merger, settling into a single, large, featureless elliptical galaxy, often nicknamed Milkomda. The elegant spiral arms we know today will be gone forever, stirred into a new shape by the ultimate mixer of gravity. This fate is not unique, it is the standard story for galaxies in a crowded universe. Our own existence within the Milky Way places us inside a living chapter of this epic, a slow-motion event that reminds us that even the grandest structures in the cosmos are in a constant, graceful state of change. That immense galactic merger will stir the gas between stars into a frenzy, but on a smaller, more violent scale. A single black hole can orchestrate its own brilliant spectacle as it feeds. When a black hole pulls in material from a companion star or a surrounding cloud, that matter does not fall straight in like a stone down a well. Instead, it forms a whirling, superheated structure known as an accretion disk. Picture a cosmic drain, but one where the water spins at nearly the speed of light, glowing with the heat of a billion suns. As gas and dust are pulled inward by the black hole's immense gravity, they begin to orbit much like water circling a drain. But this is not an orderly procession. Different streams of material moving at different speeds create tremendous friction, colliding and grinding together. This friction, combined with the crushing pressure of gravity, heats the material to temperatures of millions of degrees, causing it to glow fiercely across the electromagnetic spectrum, from X-rays to visible light. The result is a luminous, flattened donut or torus of plasma spinning around the point of no return. What we see from Earth depends entirely on our viewing angle. If we look directly down on the disk, face on, we see the brilliant central region and the swirling patterns of hot gas. But if our view is edge-on, the thick outer rim of the donut can obscure our direct line of sight to the very center. This orientation helps explain why some supermassive black holes, like the one in galaxy M87, appear with a brilliant jet shooting from its poles, while others seem more quiescent. The disk itself is a cosmic laboratory. By studying its rotation speed and temperature, astronomers can weigh the black hole at its center, calculating its mass with remarkable precision. The inner edge of the disk, where material makes its final, fatal plunge, is where Einstein's predictions become visible. The incredible gravity warps spacetime so severely that light from the back of the disk is bent upward and over the top, meaning we can actually see parts of the underside. In extreme cases, this creates a double image of the disk, a mirror in the sky forged by gravity itself. These luminous rings of doomed matter are more than just a light show. They are the clocks and scales by which we measure the invisible, proving that even the darkest hearts in the cosmos can be outlined in fire. While black holes paint the sky with light, an invisible rain of particles constantly falls upon us from deep space. These are cosmic rays, not rays of light at all, but atomic fragments traveling at nearly the speed of light. They are mostly single protons, the nuclei of hydrogen atoms, though they can also be the nuclei of heavier elements like iron, all stripped of their electrons and hurled across the galaxy by unimaginable forces. Their origins are the most violent events in the cosmos. The primary source is the shock waves from supernova explosions, the catastrophic deaths of massive stars. These expanding shells of debris act like natural particle accelerators, far more powerful than anything we can build on Earth, whipping charged particles to velocities that approach the ultimate speed limit. Some of the most energetic cosmic rays may come from even more exotic sources, like the jets of active galactic nuclei or the mergers of neutron stars. When one of these high-energy bullets from space strikes the top of Earth's atmosphere, it does not simply penetrate. It collides with a molecule of nitrogen or oxygen in a spectacular, cascading explosion of secondary particles. This creates an atmospheric shower, a downward spray of electrons, positrons, muons, and gamma rays that can spread over many square kilometers by the time it reaches the ground. Every second, about one of these secondary particles passes through your body. This constant, silent drizzle has real consequences. For astronauts venturing beyond the protective shield of Earth's magnetic field and thick atmosphere, cosmic rays pose a significant radiation hazard. On a journey to Mars, an astronaut's body would be continuously peppered by these high-energy particles, increasing the risk of cancer and potential damage to the central nervous system over a long mission. Even at high altitudes, airline pilots and flight crews receive a higher annual dose of radiation from cosmic rays than people on the ground, a factor carefully monitored in aviation safety. On a grander evolutionary scale, this particle rain has been a subtle but persistent player in the story of life itself. A tiny fraction of the genetic mutations that occur in living organisms, the raw material for evolution, are caused by cosmic rays penetrating the atmosphere and striking DNA. Over billions of years, this external source of mutation has contributed, in a very small way, to the genetic diversity of our planet. We are not just living under a sky of stars, but within a constant storm of atomic shrapnel from those very stars, a reminder that the cosmos interacts with us in ways both invisible and profound. The silent, ancient surface of the Moon is not as still as it appears. It trembles with its own seismic activity, a phenomenon we call moonquakes. For years after the Apollo astronauts left, the instruments they planted continued to listen, and they revealed a world that groans and shifts. Between 1969 and 1977, seismometers at 4 different landing sites recorded over 13,000 seismic events. These were not like earthquakes here on Earth, but they proved our satellite is far from geologically dead. The causes of these tremors are varied. Some are the deep, resonant shudders triggered by tidal stresses. Just as the Moon's gravity pulls on Earth's oceans, Earth's far stronger gravity flexes the solid body of the Moon itself. This stretching and squeezing as the Moon moves through its elliptical orbit builds up stress that is eventually released as a quake. Others are more superficial, caused by the brutal temperature extremes. For 2 weeks, the lunar surface bakes in sunlight at over 100 degrees Celsius, then plunges into a 2-week night of minus 170 degrees. This 500-degree swing causes the crust to expand and contract violently, creating sharp thermal quakes that ring out like a bell being struck. Then there are the obvious triggers: meteorite impacts. The constant peppering of space rocks from tiny grains to larger boulders sends vibrations echoing through the lunar interior. The data showed something unexpected. Moonquakes can last much longer than their terrestrial counterparts. On Earth, quake vibrations are dampened quickly by water and the loose, fractured layers of our crust. The Moon, however, is dry and rigid, more like a giant, solid crystal. Seismic waves can bounce and reverberate inside for an hour or more, ringing like a gong after it has been struck. This has profound implications for the future. If we are to build permanent bases, habitats, or mining operations on the Moon, we must understand this seismic landscape. A strong, deep moonquake could potentially trigger landslides in the loose regolith or damage delicate structures. Knowing where and how often these quakes occur is essential for choosing stable ground, just as we map fault lines on Earth. The old Apollo data is now being revisited with new urgency, guiding the plans of Artemis and other lunar ambitions, reminding us that to live on another world, we must first learn to listen to its hidden rhythms. The quiet tremors of the moon are a whisper against the cosmic scale of structures so vast they defy comprehension. Among them, a discovery from 2013 shattered our expectations of how the universe organizes itself. Astronomers mapping the locations of gamma-ray bursts, the brilliant flashes from the depths of massive stars, noticed an impossible pattern. These beacons were not scattered randomly. Instead, they revealed a staggering concentration, a filament of galaxies so enormous it was promptly named the Hercules Corona Borealis Great Wall. This is not a wall of bricks and mortar, but a gravitationally bound tapestry of galaxy clusters and superclusters, a cosmic continent stretching roughly 10 billion light-years across. To grasp that scale, consider that a single light-year is about 9.5 trillion kilometers. This single structure is so long that a beam of light, the fastest thing in the universe, would need 10 billion years to travel from one end to the other. That is more than half the age of the universe itself. Its existence stands in direct tension with a foundational idea in cosmology, the cosmological principle. This principle states that on the largest scales, the universe is homogeneous and isotropic. In simpler terms, if you zoom out far enough, the cosmos should look roughly the same in every direction and contain no giant defining landmarks. Matter should be spread fairly evenly, like raisins in a well-mixed loaf of raisin bread. The Hercules Corona Borealis Great Wall is not a raisin. It is an entire cluster of raisins fused together into a structure that should not exist according to our standard models. Finding something this gigantic forces a profound question. Is our understanding of the universe's large-scale structure incomplete, or did this wall form through processes we have not yet accounted for in the early universe? Some theories suggest it could be a remnant of primordial sound waves, frozen ripples from the Big Bang that seeded slightly denser regions which grew into these colossal filaments over billions of years. Others wonder if it hints at something about the mysterious nature of dark matter and dark energy, the invisible scaffolding and force that govern cosmic expansion. This Great Wall is more than a record holder. It is a boundary marker for our knowledge, a silent, sprawling challenge written across the sky, reminding us that the universe may yet hold architectures of such immense scale we can barely conceive of them. That same Martian dust that sculpts the landscape also paints the sky in a color we would never see at home. While our sunsets blaze with fiery reds and oranges, a sunset on Mars is a cool, ethereal blue. It is a complete inversion of the palette we know, and the explanation lies in the very air or lack of it and the dust suspended within. Here on Earth, our sunsets are red because of a process called Rayleigh scattering. Our atmosphere is thick with nitrogen and oxygen molecules, which are very efficient at scattering the shorter, bluer wavelengths of sunlight in all directions. This scattering is why our daytime sky is blue. At sunset, when sunlight must travel through a much thicker slice of atmosphere to reach our eyes, almost all of the blue light gets scattered away, leaving only the longer, redder wavelengths to paint the horizon. Mars flips this script entirely. The Martian atmosphere is incredibly thin, only about 1% as dense as Earth's. With so few gas molecules, Rayleigh scattering is minimal. The daytime Martian sky, as a result, is not a deep blue but a pale, butterscotch or pinkish hue. This color comes from the true artist on Mars' fine iron oxide dust. This dust, finer than flour, is perpetually suspended in the atmosphere. When sunlight enters this dusty sky, the physics changes. The dust particles are much larger than gas molecules. Instead of scattering blue light most effectively, these larger particles scatter the longer, redder wavelengths forward toward the direction of the sun's travel. The shorter blue wavelengths, however, are scattered more to the sides. So, as the sun dips below the Martian horizon, you, the observer, are positioned perfectly in that zone of sideways scattering. You see the blue light scattered toward you, while the red light is cast forward, away from you. creating a glowing blue halo around the setting sun against a darkening sky. We have witnessed this surreal spectacle not through artists' renditions, but through the lens of science. The rover's curiosity and perseverance have both captured high-definition color videos of Martian sunsets. In these clips, the sun is a small, bright disk, not the swollen orb we see through Earth's thick air. As it descends, a distinct blue glow intensifies around it, while the sky above transitions into layers of cool color. It is quiet, serene, and profoundly alien. This simple difference in sunset color is a direct window into the environmental soul of another world. It tells us of the thin air, the omnipresent dust, and the unique scattering properties that shape the Martian experience. To stand there and watch that blue sunset would be to know, in your bones, that you are standing on a planet with its own rules of light and atmosphere, a world that has crafted its own kind of beauty from rust and thin air. The serene blue sunset of Mars is a spectacle tied to a star, but not every world is granted such a permanent anchor. Drifting through the profound darkness between stars are orphaned worlds, planets that have been violently evicted from their home solar systems. These are rogue planets, celestial nomads wandering the galaxy alone, untethered from the light and warmth of any sun. Their origin story is one of cosmic chaos. In the youthful, crowded environment of a forming star system, gravitational interactions are fierce. A young planet, especially a gas giant like Jupiter, can have its orbit destabilized by a close encounter with another massive planet. This gravitational slingshot can be so powerful it flings the planet clear out of the system entirely, casting it adrift into interstellar space. Once free, it embarks on an eternal journey, a frozen voyager on a trajectory set billions of years ago. The conditions on such a world are the definition of extreme. Without a sun, its surface, if it has a solid one, is plunged into a permanent, deep space night where temperatures hover just a few degrees above absolute zero. Any atmosphere it once possessed would likely have frozen into an icy crust. Its only source of internal heat would be the faint, residual warmth from its formation and the slow decay of radioactive elements in its core. It is a lonesome existence in the ultimate cold. Detecting an object that emits no light of its own, reflects no starlight, and drifts in perfect blackness seems an impossible task. Yet astronomers have a clever tool, a phenomenon predicted by Einstein's theory of general relativity called gravitational microlensing. Imagine a rogue planet drifting silently across our line of sight to a distant background star. The planet's gravity, though small, warps the fabric of spacetime around it, acting like a tiny, cosmic lens. As it passes in front of the distant star, it bends and focuses the star's light, causing a temporary, characteristic brightening of that star from our perspective. This brightening follows a very specific pattern, a symmetric curve that reveals the mass of the foreground object causing the lensing. It is a fleeting event, lasting perhaps days or hours, but it leaves an unmistakable signature. Through painstaking surveys that monitor millions of stars night after night, teams like those working with the Optical Gravitational Lensing Experiment, or OGLE, and others have captured these rare events, confirming the existence of these free-floating planets. The implications of these detections are staggering. Based on the number of microlensing events observed, statistical models suggest rogue planets may be astonishingly common. Some estimates propose there could be billions, even trillions of these dark wanderers in our Milky Way alone, potentially outnumbering the stars themselves. Each one is a frozen time capsule from a disrupted solar system, a world that never knew a sunrise, carrying within it the untold story of its violent birth and ejection. Their silent, overwhelming presence forces us to reconsider the architecture of our galaxy, reminding us that for every planet basking in a star's glow, there may be another, forever traveling in the endless night between them. That eternal silence of the rogue planet stands in stark contrast to the iconic, and often misunderstood, symbol of humanity's greatest adventure, The American flag planted on the moon by the Apollo astronauts is the subject of a persistent myth that it appears to be waving in a breeze, proving the landing was fake. The truth, however, is a brilliant piece of engineering and simple physics. The flag was designed specifically for an environment with no atmosphere. To make it appear as if it were flying proudly in a place with no wind, NASA engineers added a horizontal crossbar at the top of the flagpole. This rod extended from the vertical pole, holding the flag out in a rigid, horizontal position, like a curtain rod holding up a drape. Without it, the flag would have simply hung limp and lifeless, defeated by the lunar vacuum. The famous footage that conspiracy theorists point to shows the flag moving after the astronauts let go of the pole. This motion is not the result of wind, but of inertia and human interaction. When the astronauts were planting the pole, they twisted and pushed it back and forth into the tough lunar soil. This imparted a rocking motion to the entire assembly. In the airless environment of the moon, there is no air resistance to dampen movement. So when they let go, that rocking and twisting motion simply continued for a longer time, slowly dissipating as the energy worked its way through the pole and the flexible flag material itself. It is the same principle as if you twisted a spring here on Earth and let it go in a perfect vacuum. It would oscillate back and forth until internal friction finally stilled it. Every subtle shift seen in the flag's position after that initial planting can be traced to the astronauts bumping the pole as they moved around the site, or the slow settling of the hardware into the regolith. The flag's design was a triumph of practical symbolism, creating an enduring image of human presence on an airless world. Its stillness now, after decades of undisturbed lunar night, is absolute, a silent sentinel in a sea of cosmic dust. Its story a testament not to deception, but to the clever solutions required to plant a piece of home in a place so profoundly alien. That flag is a human symbol on an alien landscape, but the very material that forms our bodies is itself an alien inheritance. The iron in your blood, the calcium in your bones, the oxygen you breathe, none of it was present at the beginning of the universe. In the first moments after the Big Bang, only the lightest elements were created, hydrogen and helium with trace amounts of lithium. Everything else, every atom that makes up our planet and ourselves, had to be forged later in the hearts of stars. This process is called stellar nucleosynthesis, and it is the universe's ultimate alchemy. Deep within a star like our Sun, the immense pressure and temperature fuse hydrogen nuclei together to form helium, releasing the energy that makes the star shine. But in stars much more massive than our Sun, the story does not end there. As they age and their cores run out of hydrogen, the core contracts, heating up further until it becomes hot enough to begin fusing helium into carbon. Then carbon fuses into neon, neon into oxygen, and so on, climbing the periodic table in a layered, onion-like structure. Each new fuel source burns hotter and faster than the last. In the final, furious days of a massive star's life, its core becomes a factory for heavy elements forging silicon into iron. Iron is a dead end. Fusing iron does not release energy, it consumes it. When the core becomes solid iron, the star's energy production shuts off catastrophically. Gravity, no longer balanced by outward pressure, wins in an instant. The core collapses in less than a second, then rebounds in a titanic supernova explosion, an event so powerful it outshines an entire galaxy. In that unimaginable blast furnace, for a fleeting moment, temperatures and pressures soar so high that every element heavier than iron is created, from copper and gold to uranium. The explosion then hurls this newly forged material, this enriched stardust, out into the surrounding space at incredible speeds. For billions of years, these stellar ashes have drifted through the galaxy, mixing with clouds of primordial gas. When a new generation of stars and planets form from these clouds, they are seeded with these heavy elements. Our solar system coalesced from such a cloud, one enriched by the deaths of countless earlier stars. Therefore, every atom of carbon in your muscles, every atom of nitrogen in your DNA, every atom of oxygen that fills your lungs was once part of a star that lived and died long before our sun was born. You are not just living in the universe, you are a walking, talking collection of its most ancient history. The cosmos is not a distant place you look up to. It is the very substance you are made of, a permanent connection written into every cell. From the stardust in your veins to the silent footprints on the moon, our journey through these 30 astonishing facts reveals a cosmos brimming with mysteries far beyond any classroom syllabus. We have seen planets of diamond, stars older than time, and storms that rage for centuries. We have learned that the universe is not a static museum, but a dynamic, evolving arena of impossible extremes and breathtaking beauty. It is a place where black holes paint with light, where ice hides on scorching worlds, and where the very expansion of space itself whispers of a future too vast to comprehend. This collection is more than a list of trivia. It is an invitation to shift your perspective permanently. The next time you gaze up at the night sky, remember that you are not looking at a distant, flat tapestry of pinpricks. You are peering into a deep, three-dimensional ocean of wonders. You are seeing the blue sunset of Mars in the rust-colored dust, hearing the silent heartbeat of a pulsar in the data, and witnessing the slow dance of galaxies on a collision course set billions of years ago. Let this newfound knowledge be a spark. Share the fact that most amazed you in the comments below, and let us keep the conversation about our incredible universe alive. If you are hungry for more journeys to the edges of understanding, be sure to subscribe. There are always more cosmic mysteries waiting just beyond the light. Until next time, keep looking